Okay, we're going to talk about increasing, decreasing functions and the first derivative test. The first derivative test being a test that you run using the first derivative of a function. So let's remind ourselves of decreasing, increasing, and constant parts of a function. Decreasing would mean that as you move from left to right, you keep finding values that are smaller, 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 smaller. So if on this interval from here, let's say from here, out here to up to here, um, we find that we are decreasing, going down. Here, it's all the same, so constant. And from here on out, we are increasing. We keep finding values that are bigger and bigger and bigger. So let's look at something the derivative can tell us about decreasing and increasing. Remember that the derivative tells us something about the slopes of tangent lines. What kinds of slopes are we finding here and here and here and here? Everywhere on the decreasing interval, the slopes are negative. Negative slopes. Here, what are we going to find? The constant means a flat line, means a derivative of 0. And let's just put some dotted lines. Dotted lines are so wonderful. Why don't we use them more every day? The interval on which it's increasing, we find positive, 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 really big positive, positive, nothing but positive slopes. So if I were to look at the derivative of a function, if it's negative, it's decreasing on that interval. If it's positive, it's increasing on that interval. And if it's 0, then it's constant. Or maybe it's at a maximum or a minimum or something. Okay? So, how very wonderful. If f prime of some c is greater than 0, then it is implied that f is increasing. If f prime of c is less than 0, it's negative, that would mean that f is decreasing. And if f prime of c, the derivative at some point is equal to 0, that would imply that f is constant. Isn't that cool? Okay. But that's not completely the first derivative test. Let's look at why. Let's bring critical numbers into this and see why they're so nice. Okay, so for a critical number, what could be happening? Let's say that for a critical number, it could be undefined or 0. So maybe I could have this happening. That'd be undefined. Maybe for another function, like this could be happening. There's no derivative this way. Or more different yet, there's no derivative like this. That's undefined. Okay. What else could be happening? This could be flipped upside down. That could be happening. There could be a hole. You could put a hole there. Okay. So all of these things could be happening at C, or at a critical value, or it could be 0. So it could be going like this and have a maximum. It could go like this and have a minimum, or if it could also go like this, but then keep going. I'm running out of colors here. Oh, I got one more here. Or it could just come the other way and do a leveling off thing in that direction. So hopefully you watched all of that, and if you come at the end, that looks like a jumbled, terrible mess. But we could have those examples where there is no derivative, so that the derivative is undefined, and that's why it's a critical value. Or we get a critical values where the slope is 0. Okay. So let's look at only continuous functions, okay, because that's what the first derivative test cares about. We're going to look at only continuous functions. and see what we can see about the derivative and increasing and decreasing and critical numbers and all sorts of different stuff like that. So let's say that we have a critical value here. And for continuous functions, let's see the different possibilities. Well, two of our favorites is if we have a maximum or a minimum, right? And that could happen this way too. You could have a cusp like that. And then we could also, though, have this going on or this going on. Okay. But let's relate it all back to increasing and decreasing, positive and negative slopes. For this one here, hopefully you can see these as all different functions. This is the example where we have a nice differentiable function everywhere, and we get a maximum. Let's see what the derivative would tell us about this function on either side of the critical value, right? Because all of these have this critical value right smack dab in the middle of them. So on this side we would have positive slopes and an increasing function. Over here we'd have negative slopes and a decreasing function. So we would know that at this critical value, and keep in mind that these are continuous functions, so we don't have any of this going off into infinity like asymptotes or anything like that. It's continuous. So we know that it was going up, right? If we never saw the graph and we just took the derivative and examined just the numbers, and we looked at the derivative, and we see that it's positive right here, and it's negative over here. So at this critical value, we know we have a maximum because it's going up and then it's coming down. We know it's continuous, so that we know at some point it stopped going up and started coming down, and right at that point we have a maximum. Likewise, this one started with some negatives and went to positives. Excuse me for that. So it started coming down, and then we know after the critical value it started coming back up, so we know we have a maximum. Same for this one. This was positive slopes, went to negative slopes, maximum. Negative slopes went to positive slopes, we got a minimum. Here, this is how we get to tell whether or not we have a maximum or a minimum, or we don't have a maximum or a minimum. Over here we have positive slopes, and then we get to a zero slope, and then we go from the zero slope back to positive slopes again. And this one likewise goes from negative slopes to negative slopes. Okay, so that's what the first derivative test is all about. For a continuous function on some interval, I find a critical value, and then I look on either side of the critical value to find out. This is why I do it, to find out if there's a maximum or a minimum or neither. Neither right here. Just a leveling off. Okay? That's the whole idea. That's why we do the first derivative test. Alright, so let's start with number 4. To negative x plus 1 squared. So, let's see, identify the open intervals on which the function is increasing or decreasing. And we'll not draw the graph yet. I mean, that's sitting right in front of you, but let's use the calculus, since that's what we are in this class to do. We're going to find the open intervals on which the function is increasing or decreasing. Now keep in mind that a function is going to keep on, if it's increasing, it's going to keep on increasing, assuming that it's continuous, until it gets to a critical value, which is basically, the short version of the story. It has to either go to 0, and then it could either go down this way, or it could keep going up this way, or it should be undefined, which means it would get to a point and come back down, or like get to a point and go like that and keep increasing. But in any case, it's going to keep increasing or keep decreasing until it gets to a critical value. So critical values are of a lot of interest to us when we're doing all this. Let me take all these away. There we go. So let's find the derivative and talk about some critical values. So y prime is equal to negative 2 times x plus 1 using the chain rule times the derivative of the inside, which is just 1. So there we are. So y prime equals negative 2x minus 2. Where is this 0 or undefined? Well, it's never undefined. We know enough about lines to know that this would be a line if we graphed it, and that this is everywhere defined. So it could be 0, though. So then x would be 1. If x were 1, this would be 0, and therefore the derivative would be 0, and this would be, well, apparently we'd have this flat tangent line. So let's find out, let's think about all the things that could be happening. This is going to be good. This is going to be really just fantastic right now. At x equals 1, we have a tangent line of 0. So here's 1, and let's say that right here is our tangent line of 0. It could do one of three things, four things. It could go like this. It could go like this. Okay. It could come down and have a minimum, or come up and have a maximum. Okay. Any of those four things could happen, and let's find out what happens by finding out, well, if it's a minimum, it's going to be decreasing then increasing, negative slopes and positive slopes. If it's a maximum, positive slopes and negative slopes. If it's just goes and levels off and goes like that, then it's positive then positive, and the other way is negative then negative. Let's find out. All we really have to do is pick some point to the left of this and to the right of this and see what the derivative is. So let's see. Let's say y prime at 0. That's on the left of this, and 0 is so nice to use. So it's negative 2 times 0 minus 2. That'd be negative 2. We have a negative derivative. Negative derivative means negative slopes. So let's see, what did I do wrong? It should be negative 1. Negative 1. So it's at negative 1. So this turns out, 0 turns out to be now on the right of negative 1. So we have negative slopes to the right of our negative 1. So we know, let's see, let's kind of draw this thing. We know negative 1 is this critical value. And so, and we know that it's, it's 0 here. And so it either it comes up in maximum, minimum, whatever, one of these four things. We know here there's a negative slope. Okay. And let's look at y prime at negative 2. It's just to the left of negative 1. So this is negative 2 times negative 2 minus 2, and we get negative 4, or no, positive 4 minus 2, and so we get a slope of positive. Just this is all that matters. Right out in front, is it positive or negative? This one's negative, so we get negative slopes. This one's positive, so to the left of the of the critical value, we have positive slopes. So we've got positive slopes over here, negative slopes over here, a slope of 0 somewhere in here, and so it could conceivably look something like this. Okay, and now keep in mind, all we're making remarks about, this looks like a sad frog. The two eyes and a thing and a mustache. Anyway, all we're saying is something about the slopes. These slopes are positive, these slopes are negative, this slope is 0. We haven't said anything about where the function is, how big the function is. And you can see that what I've drawn fits what we have discovered. But if you look at the graph in your book, the graph actually touches the x-axis. It doesn't go where I've put it. It goes down here. Okay? That's a sad frog with a double chin. So that is what we're saying about the first derivative test. Doesn't say anything about the function itself and where it is and how much it's worth. Just about the slopes. Okay? And keep in mind throughout all this, in section 3.6, we're in section 3.3 right now, it's going to put everything together and we're going to start sketching these curves with all the stuff that we know. Okay, so one of the things that we know right now is about the slopes and whether or not we're going to have maximums or minimums at certain critical values. Okay, that's all we're finding out. let's do number 6 as another practice here. F of x is equal to x to the fourth minus 2x squared. F prime of x equals 4x minus 4x. 4x to the third minus 4x. Alright. Alright, we're going to first look for some critical values. So where is 4x to the third minus 4x equal to 0? Well, we factor out an x, a 4x. And we're left with x squared in here, minus 1. And so x could be equal to 0, right? 4x equals 0 divided by 4x equals 0. Or x could be equal to plus or minus 1. They made that nice and easy for us. We have critical values here. And we know the derivative is 0. We know we have these horizontal tangent lines, right? At, let's put some red in here, at 0 and at positive 1 and at negative 1, we know something's happening. We know that we have these horizontal tangent lines. Horizontal here, and maybe it's horizontal here and here, something like that. So let's find out what's going on, right? All sorts of stuff could be happening here. It could be a maximum and then a minimum and then a maximum again, or it could be like this. It could be an M or a W, or it could kind of level off like this and go up and then have a maximum. It could do all sorts of stuff. So we're going to find out, what's it do? Is it coming down here? Is it going up here? Is it going up here again? And we're going to find that out with the derivative. Okay, let's find out. We got to test here and here and here and here. So we're going to test to the left of negative 1. So let's test with negative 2 equals negative 2 to the fourth minus 2 times negative 2 squared. This one is 16. This one is 4. And 4 times 2 is 8. 16 minus 8 is... and let's make sure I've got the 16. Let's see, 4 times 2. What am I... Got something going on here. Okay, I took a moment to collect my thoughts and discovered, of course, that I'm using f of x. I don't care about f of x. I cares about f prime of x. Remember that we're asking about the slopes of the tangent lines. So 4 times negative 2 to the third minus 4 times negative 2. So this is negative 2 to the third. That's negative 8 times 4 is negative 32. Negative 32 plus 8 is, well, it's negative. It doesn't really matter what it is. It's negative. That's what we're worried about. So let's negative right there. Negative 2. F prime of something between negative 1 and 0. We can't plug 0 in because it's a critical value. So let's go with negative 1/2 equals 4 times negative 1/2 to the third minus 4 times negative 1/2. This is going to be negative 1/8. 4 times negative 1/8 is negative 1/2. And this is, let's see, 4 times negative 1/2 is negative 2 times, a negative. So positive 2. This is positive. So here we have a positive slope. Now somewhere between 0 and 1, that's going to be 1/2. F prime of 1/2 is 4 times 1/2 to the third minus 4 times 1/2. Okay, this is going to be positive 1/8, positive 1/2, same as this one, it's just positive this time. Minus 2 is equal to negative 3/2, and that's negative. And our last one we're going to pick, I would say 2. A nice whole number makes life grand. So 4 times 2 to the third minus 4 times 2. Yep. And that's 8. That's 8 times 4. That's 32. Minus 8. That's, well, positive. That's all that matters. It's positive. Positive. So we have negative slopes and positive slopes and negative slopes and positive slopes. So here, somewhere in here, we've got ourselves a minimum, we've got ourselves a maximum and a minimum here. Okay, so this is useful information if we're going to sketch the graph, to know that it's going to, come up and do this, something like this, and something like this. Not to say that all this happens way down here, or even that it happens up here. We don't know about where this stuff is happening, as far as y values. We could find out. We could plug these values into the function. We'll do that later. But right now, we're just finding out there's a minimum, there's a maximum, there's a minimum at these values. And not that necessarily that the maximum is here, or it's here, or it's here, but that it is found at 0. Okay. Let's go with number 12 next. H of x equals 27x minus x cubed. Okay. We're going to take the derivative because we love the derivative. We love taking the derivative. We love saying the word derivative. We eat, sleep, and breathe derivative. So 27 minus 3x squared. Alright. And remember that we're interested in this, the increasing and the decreasing, and that translates to positive and negative slopes. And we know that this change in positive to negative could happen only at a critical value. So we're looking at critical values here. Where would this be equal to 0? So this is what we're aiming to find out. So at plus or minus 3, we have critical values. We have slopes of 0. And we're wondering again what happens. Is it like this? Is it like this? Is it like this? That'd be weird. Okay, so what's going on at this point, at 3 and 3? And is it increasing here and decreasing there and decreasing some more? Let's find out. It matters about the derivative. Is the derivative positive or is the derivative negative? It tells us if it's increasing or decreasing. So let's look at the derivative here and here and here. Here is negative 4, so let's go with h prime of negative 4. That's 27 minus 3 times negative 4 squared. Alright. And, well, this is going to be, well, let's find out. Sometimes you can just kind of look and see, but you might as well just go ahead and plug it all in. So this is going to be 48. 16 times 3 is 48. 27 minus 48 is negative. That's all that really matters. This is negative here. H prime of something in between the two critical values, I like 0. That's going to be 27 minus 0, so 27, so positive, that's what matters, positive. Something over here, maybe 4. Something manageable. 27 minus 3 times a positive 4 squared. And so this is going to be 48 again. It's going to be the same. It's going to be negative. So again, negative. So it seems we have negative slopes here. We've got some slope of 0. We come up this way and we find a slope of 0 and some negative slopes. So our graph's going to look something like this somewhere. This could be whether I draw the function here, or if I drew it here, or I drew it here, or up there, these all have these attributes. Negative slopes here, positive here, negative here, 0 at 3 and negative 3. Okay, so remember that we don't know necessarily where the function is, only what it's doing at that point. Okay. Let's try 14. Alright. So we'll find the derivative. That's 1 plus negative 4 over x squared. And then we ask ourselves, now, where's the derivative undefined? That would be an interesting question. This is negative, so 1 minus 4 over x squared. Okay, where would it be undefined? That would be anywhere that we find, trouble spots. And a trouble spot with a fraction is if the derivative, or the denominator of that fraction is 0. So that could happen. If x is 0, then we have an undefined slope. So, that's interesting. It's an interesting thing. So then we also want to find out when is the derivative equal to 0. And let's see, 4 over x squared equals 1, x squared equals 4, x equals plus or minus 2. So here we have critical values, here we have a critical value. Now keep in mind, all it's asking us is to find the intervals where the function is increasing or decreasing. That's all it's asking for. So the things that we know is we have a critical value here. So some kind of something happens with the slopes and the derivatives. And over here at positive 2, something happens as well, and over here something happens as well. Here and here, we have slopes of 0. Here we have an undefined slope. And we're not concerned with whether or not that's an asymptote, or if that's a point or whatever. All we're looking for is increasing or decreasing on these intervals. So let's find out about them. So on this interval, let's say we go to negative 3. Let's find something out about the derivative at negative 3. Equals 1 minus 4 over negative 3 squared, so 9. So 1 minus 4/9 is that positive or negative? That's all we really need to worry about. It's 5/9, so it's, use a colon here, some kind of conclusion. It's positive. So this is positive. It's increasing on this interval. The interval from negative infinity till negative 2. Right? Let's test in here between 0 and negative 2. So negative 1 seems like a super good one. 1 minus 4 over 1, because negative 1 squared would be 1. And this is going to be negative 1 minus 4. So it's negative, which means it's decreasing on this interval from negative 2 to 0. Let's go to positive 1. Y prime of positive 1 equals 1 minus 4 again. Right? 1 minus 4 over 1 again. So this is again negative. It's decreasing from 0 to 2. And this last one we'll put in a positive 3. Y prime of positive 3 equals 1 minus 4 over 9 again. So positive. Let's see. Positive, increasing, and the interval would be from 2 to infinity. Okay. There you go. There's finding increasing and decreasing intervals. Okay. Now I'll go with number 18. 18 gives us this whole step processes. Find critical numbers. Find open intervals in which the function is increasing or decreasing, and apply the first derivative test to identify all relative extrema, and then use a graphing utility to confirm your results. So first we'll start with writing it down. It's always a good step. And then the derivative is also always of interest. And then where the derivative, basically tells us we have critical values. So where it's 0 and where it's undefined. So it would be 0 at -2, -4, minus 8 divided by 2, -4. We have a slope of 0 at -4. So we know, this is nice. When the slope is 0, that's a nice deal. Because it's either going to be a maximum, minimum, level off and keep going, level off and keep going. One of those four things. We're going to find out which it is by applying the first derivative test. We also kind of have a check because we know this is a parabola, so we know it's either coming like this or going like this. And we also we know it's a positive leading coefficient, and so we know it opens up, and so we really know there's a maximum or a minimum here at -4. But let's practice. It's good to get practice. F prime of something to the left of -4, so let's go with -5, is equal to -10 plus 8. That's negative. So negative slopes, it's decreasing on this interval. F prime of something to the right of -4. I like 0, always like 0. That's 8. That's positive. Okay, so we know that at this point we have a minimum, and that's what it was asking us to do. And if you want some confirmation that you did this all correctly, you could graph it on your graphing calculator and see that there is a minimum at -4. Let's go to 22. Gonna do the same kind of thing on 22. What's the third? 6x squared plus 15. Alright, find the derivative. Always want to start with that. 3x squared minus 8x. Where is the derivative? 0 or undefined? It's 0. Well, we're about to find out. Take out an x. So at x equals 0 and x equals 8/3, we have something happening. We have a slope of 0 at x equals 0 and x equals 8/3. Okay, so that's like almost 2. Or it's almost 3. Excuse me. It's almost 3. We've got a place here and a place here, a place here. 3 different intervals to test, right? And so we'll do f prime of something over here, -1 seems good, equals 3 times -1 squared minus 8 times -1. So this is 3 plus 8. This is positive right here, increasing, right? And then f prime of something over here between 0 and 8/3, 8/3 being between 2 and 3, so how about 1? 1 is nice and manageable. So 3 times 1 squared minus 8 times 1. This is going to be 3 minus 8. That's going to be negative. F prime of, let's say it's almost 3, so let's just go ahead and use 3 since it's just to the right. So 3 times 3 squared minus 8 times 3. This is what I like about these sometimes. Like this is 9 times 3. This is 8 times 3, so this isn't quite as big as this, so I know it's going to be positive. That's always fun. Okay, and so I know that it's increasing. There's some zero slope somewhere in here. There's negative slopes in here. Zero slope, positive slopes. So this could work. This could work. This might be it. Right? Something like that you're going to find. If you graph it, it's going to look something like one of these, somewhere. I don't know. It could be way up at 100. I'm not sure. Actually, I'm sure that it's not, but could be. So, sorry, I just got distracted by a pop-up. That was very unprofessional. You can take it out of the pay I get for making these videos. Right, here we go. We want to take the derivative. Always a fun time. So, derivative of this, 1 times x squared, excuse me. Okay, well, I must be going. So, it won't be a big deal for you. It'll just be continued on the video below this one. Or maybe I'll edit them together. I don't know yet. But that's it for now. Except for it's just a few seconds for you, but hours for me. That's cool. That's the internet. Bye.